In this module, we're going to start to calculate some of those changes in entropy during the course of the reaction by looking at the standard molar entropies of the reactants and the products and finding the difference between the two. So entropy changes, because they are a state function, right? State functions, the only thing that matters is where do we start and where do we end. It doesn't matter if I go through that process in one big step or 10 little steps. All that matters is where I start and where I end. So elevation is an example of a state function. I could start at the first floor and take the elevator to the fourth floor or take the stairs to the fourth floor. It doesn't matter. My change in elevation would be the same. Entropy is the same way. All that matters is what was my initial entropy and what was my entropy at the end of the reaction. So what's my entropy of the reactants and what's my entropy of the products? The difference between the two is my change in entropy during the course of the reaction. And because entropy is in a molar value, we need to incorporate how many moles of products and reactants we have to determine what's the overall entropy, the total entropy of my reactants, and the total entropy of my products. And so that's what this calculation means. My change in entropy equals the summation of, so the sum of all the entropy of the products minus the sum of all the entropy of the reactants, where we're going to get these coefficients right from the balanced chemical equation, right? Because the entropy is given as a molar quantity. So if I have 10 moles, I have 10 times the entropy. And so here's an example, and I know none of you would let this happen, but say you open a bottle of wine and you don't finish that bottle of wine in one sitting. What happens is that wine gets exposed to air, and within the air there are certain bacteria that will oxidize the alcohol, the ethyl alcohol in that wine. They'll oxidize it to acetic acid, basically giving you vinegar, red wine vinegar if you were drinking a bottle of red wine. Calculate the entropy change for that reaction. And before we start, right, initially we were looking at entropy by changing moles or by changing phase. Right, let's look at this reaction and just make a guess as to what's going to happen to the entropy. Will the entropy increase or decrease during the course of this reaction? We have a liquid reacting with a gas to give us a liquid and a liquid. And we have 1 mole of ethanol, 1 mole of oxygen producing 1 mole of acetic acid and 1 mole of water. So there is no change in moles, so I can't use that to determine is this reaction going to cause an increase or decrease in entropy. However, I do go through a phase change. I start with a liquid and a gas, and I end with a liquid and a liquid. So based on that, we might guess that we'd see a decrease in entropy, right? The reaction might result in a decrease in entropy, right? And that's kind of odd because we've said for a reaction to occur, and a reaction to occur spontaneously, there needs to be an increase in entropy. Well, this reaction certainly happens, right? Ethanol certainly gets oxidized in the presence of oxygen to form acetic acid. That reaction happens every day. Let's take a look, right, to help get a better understanding of what we might be missing. So let's just officially calculate that change in entropy before we get too far into this problem. And so to calculate that change in entropy, we just need our change in entropy equals the summation of all the moles of products and the entropy of those products minus the summation of how many moles of reactants and the entropy of those reactants. And here are the molar entropies for the ethanol, the oxygen, the acetic acid, and the water. So in the next slide, we're going to start plugging those entropies into this total calculation. So for this calculation, my change in entropy would equal the summation of, well, the entropy for my products. So my products are acetic acid and water. So I have 1 mole of acetic acid at 160 joules mole plus 1 mole of water at 69.9 joules per mole Kelvin, minus the summation of the entropy of my reactants. My reactants are ethanol and oxygen. So I have 1 mole of ethanol, and that entropy is 161 joules mole Kelvin, plus the entropy of 1 mole of oxygen at 205 joules mole Kelvin. So the important thing here, why I had to take into account, right, N and M, those are the coefficients from the balanced chemical reaction. So I had 1 mole of acetic acid. When I multiply, right, moles cancel out. I had 1 mole of water. When I multiply, moles cancel out. 1 mole of ethanol, moles cancel, and moles cancel. So it doesn't change my number, but it does change the units, and that's why I work through that step. So we have the delta S equals the summation of 160 joules per Kelvin plus 69.9 joules per Kelvin minus the summation of 161 joules per Kelvin plus 205 joules per Kelvin. So the biggest mistakes people will make here will be simply addition and subtraction mistakes. So please always keep track of your sign and know whether we're adding or subtracting. So I'm going to add those two together, and I get approximately 229.9 joules per Kelvin minus the entropy of my reactants, which is about 366 joules per Kelvin. So now I can subtract those two, and I get a change in entropy for this reaction of approximately negative 136 joules per Kelvin. Right, and on the onset, we decided, right, we made the estimate that this reaction would result in a decrease in entropy because of our phase changing. We are going from a liquid and a gas to a liquid and a liquid. So we're making 2 liquids. That's a decrease in entropy because we're going and taking a gas and making it into a liquid. And we confirm that by calculating a decrease in entropy for this reaction. So let me then ask you again, right? We must be missing something because I said for a reaction to occur, there needs to be an increase in entropy, right? For a spontaneous reaction to occur, a process to occur, there needs to be an increase in entropy. We just calculated a decrease in entropy. So what component are we missing? And so that next component that we are missing is taking a look at the heat of the system, right? So that entropy needs to increase for the universe for a spontaneous process to occur. We were looking at a very localized case, and we were looking at the entropy of that system. We were kind of ignoring the entropy, what's happening to the entropy of the universe. So entropy is measured as the heat added to a system over the temperature where the heat is added. And we said that, right, for this to be spontaneous, we need to have an increase in entropy. So that means that the change in entropy, right, change in S is our change in entropy, needs to be greater than the heat over the temperature. And we know that temperature, right, the heat that we're talking about is really the delta H. What's the heat of this reaction? What's the heat that's being released or absorbed by this reaction? So we can say that our entropy, our change in entropy, needs to be greater than our delta H divided by our temperature. So now all I'm going to do is I'm going to take this and rearrange this to kind of solve for what we're looking for. We want to know if I bring together entropy and my enthalpy and the temperature, what does that value need to be? So all I'm going to do is take this equation and just rearrange it by multiplying both sides by temperature. And so temperature cancels out, and we're left with temperature times entropy is greater than my value of delta H. So I want to know, what is this value when I put all three of these together. So I'm just going to subtract temperature and my entropy from both sides. To get that 0 needs to be greater than delta H minus T delta S. And this is the equation for Gibbs free energy. And now we've added one more component to determining the spontaneity of a reaction, right? Initially, we were just focusing on what is the entropy of the reaction while ignoring the enthalpy of that reaction. What is the heat of that reaction? Because ultimately, for a reaction to be spontaneous, we need to increase entropy for the universe. So locally, we may have a decrease in entropy. Locally, we may have a negative delta S. But if that reaction gives off enough heat, if we have a large enough delta H, we're going to warm up the universe enough to result in an increase in entropy, and that reaction will be spontaneous. So taking a look at this equation again, right, all this means is that 0 needs to be greater than delta H, the enthalpy of the reaction, minus the temperature of the reaction times the entropy of the reaction. So now we're talking about the free energy, and we're going to be looking for something that needs to be, right, less than 0, because 0 is greater than that for a spontaneous process. And as I said, that's known as our Gibbs free energy, where it's basically a measure of the amount of work that can be performed from a reaction or process. Right? And it is now the standard for determining a spontaneous reaction. So now we're going to be looking for what is the delta G of the reaction, and that's going to tell us, is this reaction spontaneous or not? So we're looking for a delta G, a negative delta G will result in a spontaneous reaction, and that'll incorporate both the heat of the reaction, right, the delta H, the enthalpy of a reaction, and the changes in entropy of that reaction. Because remember, we're looking for the entropy of the universe to increase for a spontaneous reaction. So what does this mean? What does this value of delta G mean? And I would always think about it as you're this giant boulder way up here on the side of the mountain, and you're rolling down the mountain, right? So if delta G is negative, right, that's a spontaneous reaction because we're rolling down the hill. Nothing's going to stop us from rolling down the hill. We want to get to a lower energy state, and we're going to do that by having a negative delta G. So if delta G is negative, right, the reaction is spontaneous as written. The reaction is spontaneous as written. Right, we want to get to the lowest energy possible, and so we're going to do that by having a negative delta G. We're moving downhill. If delta G is 0, we've reached equilibrium. We've reached the lowest point in the valley. The boulder's not going to roll any farther. The reaction is at equilibrium. And if delta G is positive, right, then we've gone beyond equilibrium. Delta G being positive, now we're trying to go up in free energy. We're trying to increase in free energy. So delta G being positive would be us taking this boulder and trying to push it up the hill. Push it up the hill the other direction or push it up the hill back to where it started. Either way, that's non-spontaneous. So that means the reaction is non-spontaneous as written. But what it does also means is the reaction is spontaneous in the reverse direction. Right, we are trying to get to the lowest free energy possible. That's what's going to determine what direction will a reaction move. We always want to go downhill with respect to our energy. We want to go to a lower energy state. And so if we have a negative delta G, right, we are getting to that lower energy state. We are rolling down that mountain. If we are at the valley, at the bottom of that mountain, right, we've reached equilibrium. We can't go any lower. That's the lowest energy state we've found. But to push that rock back up the side of the mountain, right, that would be a positive delta G. We'd have to raise the energy of that. We'd have to put energy into that. That is not spontaneous. That would require a lot of work, but the opposite direction would be spontaneous, right? If I'm pushing it up the hill, that's non-spontaneous. Just letting go of the rock and letting it roll back down, that would be spontaneous because that's bringing us to a lower energy point. So let's take a look at this reaction. Nitrogen reacts with oxygen to produce 2 molecules of nitrogen monoxide. And the delta G of that reaction is 173.2 kilojoules. So looking at that reaction, right, what could you say about this reaction in general, given that what we just talked about? Well, to start us off, right, we have a positive delta G. So that means the reaction as written is non-spontaneous, right? That reaction is uphill. But what that means is the reverse reaction so 2 molecules of nitrogen monoxide, right, breaking down into a molecule of nitrogen and a molecule of oxygen gas, that delta G, we're going to go the opposite direction now, right? This is a state function. It only matters where did we start and where did we end. It didn't matter how many steps we took. So if I flip that reaction, I flip the delta G, right? Now I'm going down 173.2 kilojoules of energy. So the reverse reaction is spontaneous. Right, I took 3 flights of stairs up. Well, I'd have to turn around and go 3 flights of stairs down to get back to where I started. That's all that we're doing here. If we flip the direction, we flip the delta G. Instead of going up in energy, right, we're going down in energy. So I know the information for the forward reaction. I also know the information for the reverse reaction. I can flip the direction of the reaction. I can flip the sign on the delta G, turning a non-spontaneous reaction into a spontaneous reaction.